let's go to the mass dependence now. So again, look at this thing here. So if I was to just copy this and bring it down, this is what we said with speed dependence, right? What does it mean to be velocity dependent? Well, it depends on whether it's harder or easy to make the object move, have a higher change in kinetic energy. So the big difference here is that we take out velocity and now we replace mass. It's harder to make not a car, but let's say a truck go faster. And here, it's easier to make a car go faster. Because it requires smaller work and therefore a lower change in kinetic energy. It's exactly the same thing. Well, what do I mean by that? Let's draw pictures. Let's start off with this picture right here, because this picture worked out well. So here we have a car, right? Here's our car situation. So what's the big difference now? The big difference is that we have a truck. So I imagine that my truck is going to look something like this. And so when I'm looking at my truck here, we can clearly see that the big difference between these guys is that this guy has what? A much larger mass compared to this one, which has a smaller mass. So now what we want to do here is that, again, we could imagine that this truck is also moving as the same speed as the car. Now you could imagine now if I had this guy pushing on the truck, because this truck is larger, we have to be applying a much larger external force on this truck. So now if I transfer this to over here, now picture-wise, what are we seeing here? Well, we could imagine that in this situation, both of these objects move the same distance, but now what happens? Let's say that they both reach the same speed. Okay, so what I'm saying here is that in this situation, they have the same final speed. In fact, I could take the prime off because they're not. So then I asked the question, why is it easier to make the car go faster? Well, you don't have to do as much work. Why is it harder to make the truck go faster? Because you have to do a lot more work. So if I start to just draw my pictures here, then I imagine the following type of thing. So when I look at this car, that has a smaller kinetic energy, But this truck has a higher kinetic energy. And the reason why it has a higher kinetic energy is because it's mass dependent. It's harder to change its motion. So with the car, I don't have to do as much work. But with the truck, I have to do more work. So that in the end, the change in kinetic energy of the car should be smaller. Maybe I should put primes on these guys here. And then if I look at this guy, you could see that this has a higher kinetic energy. But again, looking at individual energies is not a meaningful thing. So what do I have to do only? I can only look at the change. And what I see here is that this has a lower change in kinetic energy. This has a higher kinetic energy. And once again, this and this is the only meaningful thing we can say. So it took more work, and therefore it had a bigger change in kinetic energy with the truck than the car. Again, in the language of the work energy theorem, what do we say here? Well, the car took just a little bit of external work, and the reason why is that we applied only a small external force, and that caused a lower change in kinetic energy. However, with the truck, that was a larger change in kinetic energy because, there was a bigger external work because there was a larger external force, and as a consequence, we had a big change in kinetic energy. So when we look at the difference here, this one had a smaller mass, this one had a larger mass, even though both of these had the exact same speed change. Not exact same speed change, but yes, the speed change is the same, but the mass is the one that really played the role. So again, in our language, we said this was easier to do. This was harder to do. And as a consequence, we end up with a lower change in kinetic energy. Here, we end up with a higher change in kinetic energy. And the reason why that is because a larger mass dependence caused this. That's what we mean by its mass dependence. Just one last thing before we move on to potential energy. And I think this is our fourth one right here. So let's go look at this here. So here's a question that I want to ask you. So the question reads as follows. Which requires more work to catch. A bowling ball or a baseball with the same change in kinetic energy. So in other words, we could imagine that they're going to throw a baseball at you. So let's say that this is the baseball, and they're throwing this baseball at you, and your whole goal on the baseball is that you want to bring it to rest. You want to stop this baseball. And then you have a bowling ball that you also throw, and you want to also stop this bowling ball. But the trick here is that they both have the same change in kinetic energy. So it turns out they both require the same work. And again, there's this language issue. So what actually happens here? Well, the question states here that the change in kinetic energy of the baseball must be the same change in kinetic energy in the bowling ball. And as a consequence, if it is the same, then the external work has to be the same by the work energy theorem here. So the only way this could be true here is that we have something like this. So the work energy theorem says that if I throw a ball and it has this amount of kinetic energy, and then at the end, I have 0 kinetic energy, then that means here that the only way this could be true here is that as I look at this guy, there has to be an external force operating in the opposite direction as that I move this guy some distance from there to there. So in this situation, the external work must be exactly the same as the K1 value. So this guy would be for the baseball. But what about for the bowling ball? Well, we said that their change in kinetic energy has to be the same, right? So this here is the negative change in kinetic energy. It has to be exactly the same. So in this case here, you could imagine that I have my change in kinetic energy must be the same. Therefore, the work to bring it to 0 must also be the same. So in this case, we would say that this was the bowling ball. So if I look at this in the language of the work energy theorem, we then agree then they require the same amount of work here. So then the kinetic energy of the baseball, if this is 0, right, it's got to be K2 minus K1. This is 0. And this has to be the mass of the baseball. And then if I look at the kinetic energy of the bowling ball, and this has a larger mass, the only way K1 can be the same in each of these situations here, if the velocity is higher for the baseball compared to the bowling ball. That is the only possibility. So we can then say that the baseball must be moving faster than the bowling ball. How much faster? It depends on the mass values.